Hello, welcome to our statistics learning session. Today, we'll be learning about using statistical hypothesis testing to measure the evaluation of to measure the performance of machine learning algorithm. For this, we have taken a case of breast cancer. This breast cancer case is presented in a bit confusing terms, the same way in YouTube example. So bear with me. Now let's dig into the case. The vast majority of problems in breast cancer are false positive. That is, the surgeries are performed on benign tumors. In case of breast cancer examination, we are saying that there are lots of false positive. That means the test is signaling that something is cancerous tumor, even though it is not. It is like a false alarm. We need to take control of this false alarm same way as we need to take control of type 1 error because they are both dangerous. You don't want to go through surgery if it is benign cancer. You want to do only surgery when it is a cancerous tumor. You don't want to do surgery when it's a benign tumor. You want to do only surgery when it is a cancerous tumor. In currently in a market, the test that is performed to see whether a tumor is cancer is state of art, and it has a false positive rate of 95%. 95% is false positive. So when people see a cancerous signal from the test, they don't take any chances. They don't take any risk, and they will go through surgery. Now we have a new machine learning procedure that wants to reduce the number of false positive from 95% to below. For this, we want to now our job is to evaluate whether this machine learning algorithm they have developed is actually working. To do just that, we have collected 297 cases of benign tumors. Keep that in mind, these are all benign tumors. These are not cancer tumors. These are all benign tumors, and we'll put through those cases through machine learning algorithm. How we do that? We'll take the attributes of features of patients, such as patient, blood pressure, age, and other attributes, and put it through the algorithm, and algorithm will say whether it is a tumor or not. And we did this test on 297 benign tumors, and it returned 206 of them were eligible for surgery. That is, the algorithm recommended 206 of them for surgery. Out of 297 benign tumors, there are 206 false positive. Now we need to know what is the rate of the false positive for this algorithm. For this, we need to divide 206 by 297. Let me highlight it. Let's not highlight, let's draw. Let's draw and use this pen. So 206 divided by 297. What is this? 69%? It seems the algorithm has a reduced false positive rate of 69%. Now, our job is to see whether this is by chance or some statistical anomaly or it is a true reduction in false positive rate. How do you do that? We can do that using statistical hypothesis on those numbers. For this, we need the we need to do some we need to do some statistical hypothesis. For that, we need the P, the proportion of benign tumors on which algorithm prescribed surgery, and P is what we just calculated. This is P. So for our model, we need to develop the model, and here we are we need to first define the variable here. What is a variable we need to define? We need to define x I as a IID variable, and it is a IID variable. And what is IID? What is XI? What kind of distribution does this XI have? XI have Bernoulli distribution because each case of this cancerous 269 297 cases of benign tumors are all Bernoulli because algorithm takes a look at the case and it gives either it recommends for surgery or it doesn't recommend for surgery. Either it gives a false alarm or it doesn't give a false alarm. So each of these cases is a Bernoulli process. That's why X follows a Bernoulli distribution. And what is the probability of the what is the parameter with the parameter P? And P is, we already know it is 69%. Knowing that, we need to formulate the hypothesis. What are the hypotheses we need to formulate? What is the null hypothesis here? Null hypothesis here is that what let's start with the alternate hypothesis. What we want to prove? We want to prove here is that the algorithm which we just machine learning algorithm which we just developed, it is better than current of state of art. It is better than current state of art, which is 95%. That is, we want to see that whether P is less than 95%, 0.95. We want to prove this. That's why it is an alternate hypothesis. And currently, the benchmark is it is P is greater or more than 0.95%. So we have our data model, we have hypothesis created. Now we need to start creating the test itself. Let's start from the beginning. Let's take the sample average and see whether it is less than something. Because if the sample average is less than something, then our alternate hypothesis becomes possible. It is some value here. Now we need to normalize this variable using mean and taking dividing by standard deviation and multiplying by n. We are trying to standardize this by some value. Now, this value should less than some value. We want to write a constraint such that the probability of this value less than some value should tend toward, should not be greater than alpha. That is, for all the p's that is greater than 0.95, the probability of p, that is probability of n, this formula xn minus p, p1 minus p should be less than q alpha, and this whole probability should not be more than alpha for our case. And alpha, it can be 5%, 10%, anything. That is all set. So let's calculate our p. What is our p here? The p is, we need to find the value of this expression, xn minus p, p value 1 minus p. What is n? N is 297. That's our size of sample. And xn here is 95%, 0.95, 0.69 divided by p. 0.69, 1 minus 0.69. What is the value of this? We need to calculate it now. Let me calculate it. 0.95 minus 0.69 equal to 0.26 multiplied by 295 and take the square root of this. 295, 0.26 equal to 17, and when you divide by square root of something, divide by 0.69, zero point 0.69 1. Okay, let me try to do this. What happened here? We don't need this. We don't need this. Let's delete this step. Let's use this 0.69. Now what we need is 0.69, 0.69. Let's do this. Let's do 1 minus 0.69. Do this and then multiply this by 0.69. And we need to take a square root of this, which is 0.46. Now, once we have this, we will we need to use we need to divide this value by this value. Now let's work on dividing it. Now let's clear this screen. Now let's divide this by this value here. That is 13.99. It's going to be 13.99. That is a value of this. Now our next job is to find the percentage or area under curve percentage for this 13.99. Now let's find that. Let's use our calculator here. The maximum value we have here. Let me go and check our. Let me check the. Let me check the table, and the area of percentage for this value in normal table is 10 to minus power 4. It is very less, and it is very less. Therefore, we can reject the null hypothesis and say that this test actually, this machine learning model actually works. Now, this value is really small. Is it better way to improve on this? Can we say that, let's say if you want to get this number small, how do you do that? We can say that this new machine learning model reduces the false positive rate from 95% to 70%. Then we can use that 70% and plug that in our hypothesis. Instead of 95%, we can write 70 and do 70% here. If you do that, then we'll have this in more reasonable number. This value becomes more reasonable. And then let me quickly summarize what we learned today. We learned about using hypothesis testing to evaluate a machine learning model. For that, we took the case of breast cancer, and breast cancer had the benchmark false positive rate of 95%, and this machine learning model comes along, says that it can reduce this 95% benchmark to 69%, and we use the statistical hypothesis testing to evaluate whether this claim was true or not. And as a result, we got that this claim was actually true. So that's much for today. I will see you next learning session. Thank you so much.